Hello everyone. Welcome to the Fundamentals of Analog Electronic Technology course. Today we begin a new chapter on the metal oxide semiconductor field effect transistor. The field effect transistor is a widely used semiconductor device. Understanding its operating principle, characteristics, and key parameters is vital for future practical applications, so please study carefully. In today's lecture we focus on Section 1, covering the N-channel enhancement mode MOSFET, N-channel depletion mode MOSFET, P-channel MOSFET, effects such as channel length modulation, and the main parameters of MOSFETs. Let us now introduce these topics one by one. The field effect triode is called an FET in English, abbreviated as field effect transistor. Structurally, it is divided into insulated gate field effect transistors (IGFETs) and junction field effect transistors (JFETs). Insulated gate field effect transistors are also called MOSFETs. Metal oxide semiconductor field effect transistors, or simply MOS transistors. Each FET type can be classified by the polarity of its charge carriers into P-channel and N-channel devices, depending on how the conductive channel forms. JFETs are depletion mode devices, while MOSFETs come in both enhancement mode and depletion mode varieties. The difference between depletion mode and enhancement mode devices is as follows. In a depletion mode device, a conductive channel exists even without an applied bias voltage. In an enhancement mode device, no conductive channel is present unless a bias voltage is applied. A field effect transistor, FET, is a semiconductor device that uses the electric field effect in its input circuit to control current in its output circuit, making it a voltage-controlled device. We will now use the N-channel enhancement mode MOSFET as an example to introduce the characteristics of FETs. Structurally, the N-channel enhancement mode MOSFET consists of a lightly doped P-type semiconductor substrate, commonly called the P-type substrate. Two regions on this substrate are heavily doped with pentavalent impurity atoms to form two N-type regions. A very thin silicon dioxide insulating layer is grown on the P-type silicon surface. N3 aluminum electrodes are placed on top of this oxide and the two N-type regions. The gate G, the source S, and the drain D. Since the gate is insulated from the other electrodes in the substrate, it is known as an insulated gate. Conduction between the drain and source occurs through the region under the gate oxide, called the channel. The geometric dimensions of this channel, length L and width W, are key parameters affecting FET conduction. They typically range from nanometers to micrometers, with the width generally exceeding the length, thus forming an insulated gate field effect transistor. For analytical convenience, we often use a longitudinal cross-sectional view of the FET. In practice, the substrate is also brought out as an electrode. Two p-n junctions inevitably form between the N-type regions and the P-type substrate. When no voltage is applied to the gate, regardless of the polarity of the voltage between drain and source, one of these p-n junctions is always reverse biased, preventing conduction between drain and source. This configuration defines the enhancement mode FET. This is its circuit symbol. The symbol not only represents the FET itself but also conveys two pieces of information. First, the break in the line between drain and source indicates that without an appropriate gate voltage, the conductive channel is off. This is characteristic of an enhancement mode MOSFET. If the line were continuous, it would represent a depletion mode MOSFET. Second, the direction of the arrow, from the P substrate toward the N channel, denotes an N channel FE. Having introduced the structure of the N-channel enhancement mode MOSFET, what is its operating principle? Control of the channel by the gate-to-source voltage V sub Gs, as shown in the figure. When V sub Gs less than or equal to 0 V, there is no conductive channel between drain and source. So even if a forward voltage is applied between D and S, no current flows. When 0 less than V sub Gs less than V sub Tn, the threshold voltage of the enhancement mode MOSFET, an electric field is generated but no conductive channel, called the inversion layer, forms. Thus, even with a voltage between drain and source, no current flows. When V sub Gs is greater than or equal to V sub Tn, the electric field repels holes in the P substrate away from the oxide layer, and free electrons accumulate beneath the oxide to form a conductive channel. Applying a voltage between D and S then produces current. The larger the V sub G, the thicker the conductive channel. A MOSFET that requires an applied gate voltage to generate the inversion layer is called an enhancement mode device. Control of the channel by the drain-to-source voltage V sub Ds. When V sub Gs is fixed in greater than V sub Tn, increasing V sub Ds increases I sub D, which increases the potential gradient along the channel. The potential near the drain rises, the electric field there weakens, and the channel narrows. Near the source, the potential drop and channel thickness remain unchanged. The channel thus takes on a wedge-shaped profile. As V sub Ds increases further until the gate-to-drain voltage V sub Gd equals V sub Tn, pre-pinch-off occurs adjacent to the drain. This corresponds to the OA segment of the characteristic curve, where the slope is relatively steep. After pre-pinch-off, further increases in V sub Ds extend the pinch-off region and raise channel resistance, while I sub D remains nearly constant. The curve then levels off horizontally, corresponding to the AB segment. The pinch-off point also marks the boundary between the variable resistance region and the constant current region. It is called the pre-pinch-off threshold point, located at the intersection of the dashed line and the AB segment. When V sub Ds and V sub Gs act simultaneously, in the I sub D, V sub Ds coordinate system, when the gate-to-source voltage V sub Gs is varied, each specific value of V sub Gs yields its own distinct I sub D versus V sub Ds characteristic curve. In summary, the N-channel enhancement mode MOSFET has the following characteristics. 1. Only one type of carrier, electrons, participates in conduction. So FETs are also called unipolar transistors, and they exhibit much better temperature stability than bipolar transistors. 2. The gate of a MOSFET is insulated, so gate current is essentially zero. Input resistance is very high, resulting in low power consumption. 3. The device conducts between drain and source only when the gate-to-source voltage exceeds the threshold voltage. Since the MOSFET allows gate voltage to control drain current, it is also known as a voltage-controlled current device. 4. Before pinch-off, the drain current varies approximately linearly with drain-to-source voltage. After pinch-off, the drain current approaches a constant value. Let us conclude this lesson using the N-channel enhancement mode MOSFET as an example. We have briefly introduced its structure, operating principle, the I/V characteristic curves of the N-channel enhancement mode MOSFET, and other aspects of metal, oxide, semiconductor field effect transistors. We will continue with the remaining topics in the next section. These are the key points of today's lesson. Thank you.